A little more than a year ago, I uploaded my very first video to this channel. Why? Because my prints with TPU filament were a complete disaster. Seriously, they were so bad that I thought my printer was broken. Then a miracle happened. A print profile from Printable solved all my problems. That breakthrough was too good not to share, and so this channel was born. Fast forward to today, and wow, this channel has now more than 3,000 subscribers. I just want to say a massive thank you for your support, your helpful advice and your overwhelmingly positive feedback. It's a rare gem to find such a kind and constructive community online, and I'm proud to be part of it. Honestly, I've learned so much from the maker community, and I hope I've been able to give back even a little. Now, to celebrate the anniversary of my first video, it's time to revisit flexible filaments. Why? Many comments on my first video said the Bambu Lab X1C or X1P just aren't made for TPU. Well, today we are putting 4 flexible filaments to the test on the X1C. 2 Bambu Originals, TPU for AMS and TPU 95A HF, the extra flexible eSUN TPE 83A and the ultra flexible Filaflex 60A Pro. Here's a sneak peek. Look at this. You might be thinking, okay, what you're trying to show me? This is a Banshee printed with Filaflex 60A on the X1C. And as you can see, it actually looks pretty good. So in this and the next episode, we will cover everything you need to know to print high quality TPU Banshees on your Bambu Lab printer. From the equipment you will need, to printer setup, filament calibration, and of course the final slicer settings. We've got it all. So welcome back to another Filament Showdown. Glad to have you here. Let's dive into today's episode. Let's meet the contenders. First up, TPU 95A HF, a filament I introduced in my very first video. Back then, I needed some tweaking to perform well. Today we will find out if Bambu Lab's default profile has improved enough to work flawlessly right out of the box. Next, we have Bambu TPU for AMS. This filament has a mixed reputation online, mainly because of its stiffness. We will test it ourselves and compare it to the others. Now onto eSUN TPE 83A. For my surprise, this filament prints incredibly well. I've really fallen in love with this material. However, it does require some initial setup effort. Finally, we have Filaflex 60A Pro, the king of flexibility. But be warned, printing this stuff is not for the faint-hearted. It requires extra effort, including some slight modifications of your printer setup. Don't panic, it's not rocket science, and I will walk you through everything step by step. My goal isn't just to show you settings, it's to help you understand what's happening behind the scenes, so you can troubleshoot and find your prints yourself. That's why I've splitted this topic into 2 episodes. Today we will start with TPE 83A and how to dial it in. No more relying on RecReUs settings from random comments. I will show you how to go from this to this, all on your own. And if you're only here for 60A, don't leave just yet. Check out the final chapters of this video, where I share some crucial printer setup recommendations. These will be the essential for printing ultra flexible filaments like 60A. Or in other words, everything you should prepare for part 2 of this series. Before we begin, let me clear up a common misconception. You do not need to drill holes or cut pieces out of your printer's printhead housing to print ultra flexible filament on the X1C or P1. I mentioned this up front because, honestly, this belief held me back from trying 60A for a long time. Yes, you can modify your printer, and it makes switching between filaments easier, but it's absolutely not a requirement. Before we dive into the nitty-gritty of each filament, what on earth is Shore Hardness? I stumbled upon a great comparison table online, which gives us a good indication. You'll find the link in the show notes. Our softest material, Filaflex 60A, is softer than a shoe sole, but a bit firmer than a pencil eraser. eSUN TPE 83A feels a little stiffer, similar to a leather belt. Surprisingly, Bambu TPU 95A is as soft as a golf ball. And finally, Bambu TPU for AMS, the stiffest of the bunch, is about as rigid as a wooden ruler. Okay, maybe not the best comparison, but you got the idea. Let me share 2 quick tests I did with these filaments so that you have a better feeling about the stiffness. First, I clamped all 4 into a vise. Don't focus on their droop, that's not gravity at play, but tension from being wound on spools. Here comes the interesting thing. When I give each string a little nudge, their elasticity becomes clear. Filaflex bounces around endlessly like an over-enthusiastic puppy. The others snapped back into place quickly and calmly, like adults at a party. Second, I bent each filament to see how they behave. TPU for AMS didn't break, but its deformation was almost entirely permanent. So yes, I share the opinion of some community members, this isn't really a flexible material. TPU 95A handled the bend better, with only a slight permanent kink. eSUN TPE nearly returned completely to its original shape. Filaflex, on the other hand, completely unimpressed by our bending shenanigans. This stuff is super resilient. It reminds me of those waterproof silicone gaskets from these airtight storage boxes. Alright, let's quickly cover some basics about TPU versus TPE. TPE stands for thermoplastic elastomer, a mix of rubber and plastic that combines thermoplastic properties with elasticity. TPU, or thermoplastic polyurethane, which I'm sure I just mispronounced, is a more refined, highly versatile derivative of TPE. Both materials can be used to print flexible, impact-resistant, UV-resistant, waterproof, and even somewhat chemical-resistant parts. Generally, TPE is a bit cheaper than TPU, but TPU offers superior tear and abrasion resistance. It also holds up much better in cold temperatures, staying flexible where TPE tends to stiffen. But here's something crucial. Both of these materials are highly hygroscopic. They don't just absorb moisture from the air, they suck it up like a sponge. I highly recommend using a filament dryer or another drying method. Trust me, you do not want to skip this step. In fact, in the next video I will show you just how dramatic the effects of damp filament can be. Alright, enough theory, let's print some stuff. Let's start with what I call the default flex filament, TPU 95A. I have the HF version from Bambu. HF stands for high flow, indicating faster print speed is possible. For the first test, I printed a Benji using Bambu's default settings for this filament, along with the standard 0.2mm print profile. Just for the completeness, my Bambu Studio version is 1.10.1.50 and my firmware version is 1.8.2.0. And here's the result. Not bad, but honestly not good enough. So let's try again, this time using the print profile I shared a year ago. Here's a quick summary of the key settings. So for the filament settings, max volumetric flow is reduced to 2.5 cubic millimeters per second and the retraction length is set to 1 mm. For the print settings, speed is reduced to 30 mm per second, travel and acceleration speed are also lowered. And now let's compare the results. This is a massive improvement, almost zero stringing and much better overhang quality. As some of you mentioned in the comments on my first video, these settings can definitely be fine-tuned further. To be honest, I haven't experimented much since I rarely use 95A, but in just 2 minutes you will see the key principles for dialing it in. Time for another Benji, this time with Bambu's TPU for AMS. Of course, I dried the filament before loading it into the AMS. Now, here's something crazy. The max volumetric flow is set to 18 cubic millimeters per second, which is insanely fast for TPU. The total print time for the Benji, just 53 minutes. For comparison, a Benji with default PLA settings takes about 38 minutes. But how does it look? Honestly, pretty damn good. No need for tweaks, Bambu nailed it with their default profile. Let's test how flexible this filament really is. Unfortunately, I can't deform it with my hands. It feels almost as stiff as PLA. Let's bring it to the real test, my mini vise. I will squeeze this little boat and compare it to 3 other benches, printed with PLA Basic, TPU 95A and the TPE 83A. As you can see, the PLA benchy was the first to give in. Sadly, the benchy made from TPU for AMS didn't hold up either and snapped under pressure. Only the TPU 95A and the TPE 83A survived our test. But here's the interesting part. Once I lose the vise, the TPU for AMS benchy almost returns to its original shape. Sure, the cabin broke off and there is a slight deformation on the railing, but compared to the scattered PLA benchy, this difference is striking. I left out the TPU 60E benchy for this test. After all, as you saw earlier, that one is so soft you can practically knead it with your fingers. Before we move on, I need to mention something really weird is going on with the TPU for AMS product. After printing the benchy, I removed the spool from the AMS. Later, when I tried to use it again, the printer suddenly refused to accept it. Even when setting the filament manually, I got this gem of an error message. Bambu Lab TPU for AMS is not supported in the AMS. Everything was up to date. I literally printed a benchy with this filament just days ago using the AMS. Turns out I'm not alone. Some hilarious Reddit comments pointed me in the right direction. Here's what worked for me. In the AMS settings, I checked the option Update on Startup. I closed all slicers, powered down the printer, inserted the filament and powered on again. After all filaments in the AMS were updated, I unchecked the option Update on Startup again, as it takes a lot of time if all filaments are reloaded every time. This solution worked for me, but seems to be a firmware bug. Too bad I won't be updating my firmware anymore, but that's another story. Let's take a closer look to the eSUN TPE 83A. I will walk you through all the steps it took to achieve these results. This section is especially helpful if you're unfamiliar with tools like Orca Slicer, temp towers or flow calibration. I will be honest, I avoided diving into these tools for a long time, but after giving them a try, I can only recommend setting aside a few hours to explore them. The community has developed some incredible tools that make it surprisingly easy to improve your print quality significantly. Anyway, if you're not interested in the details and just want the final slicer settings, feel free to jump ahead to the chapter Final Slicer Settings for TPE 83A. So, where did I start when I first got this filament? Like many of you, I checked out the user reviews on the product page, Amazon in my case. The filament can apparently be loaded through the external filament input, although it is recommended to unwind the spool manually, which I already found annoying. A pie plate is usually recommended and it should not be heated. For slicer settings, opinions vary. I initially went with the generic TPU print profile and based on the recommendations lowered the nozzle temperature to 230 degrees Celsius. The pie print bed temperature was set to 1 degree, effectively keeping it unheated. Before printing, I dried the filament at 70 degrees Celsius for several hours and opted to print directly from the dryer without unwinding the filament. It would drive me crazy to constantly check whether enough filament has been unwound and then risk it getting tangled. In the dryer, the spool sits on ball bearings and during my first print it seemed to work smoothly. As for my first print, a benchy, well, it didn't look great. The bow area shows clear signs of poor adhesion to the lower layer. It seems the filament is pulled back by the nozzle. We should probably increase the temperature and print more slowly. Looking at the roof overhangs, you can also see that the filament isn't bonding properly to the layers below. And last but not least, there's some slight stringing. For these reasons, I decided to print a temp tower. If you don't know what this is, you need the freeware Orca Slicer. It's made by the community for the community. You find the link in the show notes below. Make sure to only download it from the official GitHub page. There are many other websites offering the tool, but avoid downloading from them as they may contain malware. Always use the official GitHub repository. If you're now desperately searching for the download button on GitHub, scroll down the README until you find the section Download. Click the link labeled Download the latest stable release. There you will see the changelog listing all updates. Scroll all the way down to find a list of different installers. Choose the one that matches your operating system. In my case, for Windows 11, it's Orca Slicer Windows Installer version 2.2.0 exe. Once downloaded, install it like any other software. Let's start Orca Slicer for the first time. It looks very familiar since it's essentially the Bambu Slicer with a different logo. You can even log in with your Bambu account to sync all your settings and printers. At least with version 2.2.0 this still works. Once everything is set up, we can generate a temp tower under calibration temperature. We select the material and define the temperature range we want to test. My tower will range from 215 to 255 degrees Celsius. Hit OK and that's it. Now you will see this beautiful tower with each level printed at a different temperature. Let's slice the model and switch the display scheme to temperature. Pretty cool and fairly easy. Time to send it to the printer. What I didn't consider is that we are printing flexible filament. The tower is too tall and wobbles like crazy during printing, so we need to improvise. We will print multiple shorter towers instead. As you can see, the material adheres really well to the print bed. For reference, I didn't use any glue or separation layers. If possible, I prefer to avoid those since they are just create more cleanup work. Here are our 4 completed temp towers, covering the temperature range from 220 to 255 degrees Celsius. I find that the print at 250 degrees Celsius looks the best. The circular hole on the side is the cleanest at this temperature. So in the slicer, I set the nozzle temperature for other layers to 250 degrees Celsius. I kept the first layer at 230 since the adhesion to the print bed is already quite strong. I also reduced the speed for inner and outer walls to 10 mm per second before printing another Banshee. After 2 hours and 25 minutes, look at this. These 2 changes made a huge difference. The boat looks amazing. Next up, we are running a flow calibration test. This test checks whether we need to adjust the flow rate for the filament. How does it work? In the filament settings you will find the flow ratio value. For generic TPU it's set to 1 by default. The flow calibration test prints a series of small patterns, each with a slightly adjusted flow rate. The adjustment value is printed directly on each pattern. In calibration, flow rate, there are several options. They all work the same but differ in the number of samples and how the correction values are displayed. I recommend using one of the YOLO options since they provide correction values with decimal precision. I started with the YOLO Perfectionist version. Looking at the results, even the sample with the highest positive adjustment, which is plus 0.35, is still under extruded. If you are wondering how to identify under extrusion, look at the top layer. If you can see gaps between the lines revealing the layer below, that's under extrusion. The top layer should be a smooth, solid surface. To rule out filament feed issues, because remember we have not unwound the filament and maybe there is too much tension and therefore we end up with under extrusion, I manually unwinded a few meters and repeated the test. The result is identical, confirming that we can safely print direct from the filament dryer without the need to unwind the filament. So I increased the flow ratio in the print profile from 1 to 1.06 and repeat the test. Even with this adjustment, all samples still show under extrusion. I continue increasing the flow ratio until I reach 1.17. Now let's examine the results. Here's the sample from the last print with a correction value of plus 0.035. That means the flow rate here is 1.17 plus 0.035 equals 1.205. I can see the first sign of slight overextrusion. The lines are starting to overlap, creating small bulges. The sample with a correction value of minus 0.005 looks the best. This gives us a final flow rate of 1.17 minus 0.005 equals 1.165. Here's a comparison. On the left is a sample printed with a flow rate of 1, and on the right it is the optimized sample with a flow rate of 1.165. I think the difference is obvious to everyone. Next up is the pressure advance test. But what exactly is pressure advance? In simple terms, it compensates for the elasticity of the filament and the extruder system. It pushes extra filament during acceleration and retracts it during deceleration, helping to maintain consistent extrusion when print speed change. This effect is, for example, clearly visible in corners. Now, before we get into tuning, this setting can be a bit tricky because Bambu Lab uses a different terminology. I also had to do some research due to the confusion, and I hope the following explanation is accurate. In Orca Slicer, you can set the pressure advance value in the filament settings as usual. However, if you share your print profile with Bambu Studio, this value is ignored because Bambu Studio handles it differently under the name K-factor. In Bambu Studio, you cannot set the K-factor in the filament settings directly. Instead, you need to create a custom filament profile and then add a custom pressure advance profile where you can define the K-factor. But that's not all. Just selecting the custom filament when slicing isn't enough. You must also apply the setting in your device under spool settings. I will guide you through this step by step in just a moment. If you slice your model using Orca Slicer, the pressure advance value set in the filament settings will override the K-factor in the device settings. Aside from your extruder hot end combination, the optimal pressure advance value depends on several factors, including filament type, moisture content, filament age, and even color. Additionally, printing parameters such as layer height, print temperature, and speed can influence the results. For more details, I've included my sources in the show notes. Alright, let's see how tuning this value works in practice. In Orca Slicer, go to Calibration, Pressure Advance. Bambu Lab printers use a direct drive extruder, and I will start with the Pressure Advance line method. For the first test, I set the line range from 0 to 2 in 0.05 increments. You need to slice so that you can see the actual print. Once the print is finished, we analyze the results. The goal is to identify the line with the most consistent extrusion. From my test, the best results seems to be between 0.8 and 0.9. To refine the accuracy, I run a second test with a smaller range. This time I set the minimum to 0.8, the maximum to 0.9, and set the step size to 0.001. Examining the second print, I found it difficult to spot major differences between the lines. In the end, I settled on 0.868 as it appeared the most consistent. Some of you may have noticed that using the textured pipe blade for this test wasn't ideal. The surface texture makes it even harder to distinguish fine differences between the lines. To get a clearer result, I reran the test using a smooth pipe blade. When switching blades, don't forget to update the bed type in the slicer and adjust the bed temperature in the filament settings, setting it to 1 degree Celsius. For comparison, this time I used the PA pattern method instead of the line method. Again, I started with a broader range from 0 to 1 in 0.05 increments. After clicking OK, I noticed that Orca Slicer automatically adjusted some process settings, including significantly lowering the print speed. Unfortunately, I couldn't determine why these changes occurred. I decided to print it as it is and analyze the results. By closely examining the top corners of the test print with pressure advance values between 0 and 0.4, I noticed slight overextrusion at the corners. Around 0.9, The extrusion looked clean and consistent, confirming my earlier results of 0.868 as the best value. By the way, print pad adhesion on the smooth biblade is slightly stronger compared to the textured biblade. Now, what you do next depends on which slicer you plan to use. If you're sticking with Orca Slicer, you can simply enter this value under Filament Settings, Filament, Flow Ratio and Pressure Advance. If you're using Bambu Studio, however, there are a few additional steps. First, we save our filament modifications to a new preset. I call it eSUN TPU version 1. Then we need to create a new filament profile. Therefore, click the small gear icon in the Filament section header. Switch to the Custom Filament tab. Click Create New. Under Basic Info, set the vendor to eSUN and the type to TPU since there is no TPE option. For the serial, I will just enter black. In the lower section, select Copy Current Filament Preset. Then choose the printer model. I'm using the X1C with the 0.4mm nozzle, and finally select the eSUN TPE version 1 profile. Alright, we now basically just copied the filament settings we already had. Of course, we can select it from our filament list, but more importantly, when we switch to our device, we now have access to the profile in our spool settings, which was not possible before. Well, but we can't change the K factor just yet. A few more steps are required. Go to Calibration in the top menu. Open the Flow Dynamic page and click Manage Results. Click New and name it something recognizable. In my case, eSUN TPE Black. Select the filament profile you just created. Choose the correct nozzle size, which is 0.4mm, and then enter the K factor value, which is 0.868, and press Save. Now we can apply the profile in the device settings. Go to your device, open the spool settings, select the new filament profile. Under Pressure Advance profile, choose the calibration profile you just created. Confirm, and you now should see the correct K factor applied. Not exactly straightforward, but we did it. Important. If you power cycle the printer, you will need to update the spool settings each time as the setting is not saved permanently. Alright, time for one last calibration, the retraction tower. Guess what? This test helps us find the optimal retraction length. To do this in Orca Slicer, navigate to Calibration Retraction Test. I initially used the default settings, but after noticing how tall the towers were, I adjusted the end retraction length to 1. Then I simply sliced the model and sent it to the printer. Here is the result. At the bottom we start with 0mm retraction. As we move up, each ring indicates increasing the retraction length by 0.1mm. Since there is no stringing at all, I will stick with the default value for generic TPU, which is 0.4mm. That's it. For the sake of completeness, there are more calibration methods, but for this filament I would personally stop here. Let's sum up what we have done so far. Printing directly out of the filament dryer where the spool sits on ball bearings. High boil plate temperature lowered to 1 degree Celsius since the parts adhere extremely well without heating. No glue, just the bar blade. Temperature tower. We settled on 230 degrees Celsius for the first layer and 250 degrees Celsius for the rest. Flow ratio calibration. Increased flow ratio from 1 to 1.165. And pressure advance calibration. We created a custom filament profile with a K factor of 0.868. So whenever we print something in Orca Slicer, we just select our new custom filament. And if we're using Bambu Studio, make sure the filament is also activated in the spool settings and that the correct pressure advance profile is selected. Now let's put these settings to the test with another Benji print. Using our new custom filament, the default 0.2mm profile and the correct spool settings, the print takes 1 hour and 11 minutes. And here is our third Benji. Well, this looks bad. We've got dents at the bow again, and some stringing around the cabin. The bow issue isn't new, we have seen it before. The problem, we are printing too fast and the filament isn't sticking properly. In the slicer preview, using color scheme speed, we can check the print speed in this area. It's 30 mm per second. Alright, time for Bambu number 4. This time I reduced the inner and outer wall speeds to 10 mm per second. Print time 2 hours and 25 minutes. Now let's analyze the results, because we see some very interesting things. The bow is now flawless, but look at the surface. The lower part is glossy, while the upper part has a matte finish. Why? Checking the speed scheme in the slicer reveals the answer. The lower region was printed at 30 mm per second, the upper region was printed at 10 mm per second. And that's fascinating, because now we know for sure that we can control the surface finish by adjusting the print speed. If you want the matte finish, print slowly with 10 mm per second. If you don't care, you can print faster. And last but not least, then we have stringing in the cabin area. Where did that come from? In the retraction test we had 0 stringing. Well, print speed affects stringing too. When printing slowly, the filament spends more time in the nozzle and gets hotter. And the hotter the filament, the higher the risk of stringing. To prove this theory, let's rerun the retraction tower test, but this time we will slow down the print speed to 10 mm per second. And guess what? Now we see tons of stringing. So with all this knowledge, let's fine-tune our settings one last time. In Filament Settings we switch to tab Overrides and set retraction length to 1 mm, retraction speed to 50 mm per second and wipe distance to 2 mm. For process settings I aim for more fast print profile. Therefore in Speed tab I set inner and outer wall speeds to 30 mm per second and slightly reduce overhang speeds to match overall print speed. Note, bridging speed remains at 50 mm per second to prevent sagging. We don't actually need to repeat the pressure at once test since, as we remember, the PA pattern method already reduced the print speed automatically to 30 mm per second. Still, out of curiosity, I run the PA pattern test again, this time manually lowering the print speed to 10 mm per second. The results are as expected. All lines looked perfect, even with a K factor of 0. Showing no signs of overextrusion in the corner. This makes sense. At such a low overall print speed, there's minimal acceleration or deceleration, so pressure at once has little effect. If we were to push the maximum print speed, pressure at once would naturally have an increasingly significant impact in compensating for extrusion lag and maintaining clean, precise corners. And now we go for the final Bambu number 5. Here it is. And I would say this one turned out really well. Yes, there's still some very fine stringing, but honestly, I do not care because you can easily wipe it off with your fingers. Alright, that's it for this filament. As I mentioned at the beginning, I really love this material, and since I put in the extra effort up front, printing with it is now reliable and delivers perfect results. The added flexibility compared to 95A is a real game changer for certain applications, as we're about to see. Now it's time to face the final boss. TPU 60A. To be honest, when I bought this filament almost a year ago, I didn't realize that I may not able to print it with my X1C. Well, when the package arrived and I felt how incredible soft the material was, I had a sudden realization this might not work out of the box. And sure enough, when I tried loading it for the first time, I was completely disappointed. I couldn't even get the filament through to the extruder. It got stuck just a few centimeters before the print head. I started searching the internet, hoping for some solid guidance, but didn't find much. Just bits and pieces here and there. Almost every source mentioned adjusting the extruder gear tension is crucial, but that required drilling a hole into the print head housing. No way was I drilling into my printer and voiding my warranty. Fast forward a few months, my warranty has expired and RecReUs, the manufacturer of this filament, has released a great video on using their filaments with the Bambu Lab P1 series. Unfortunately, in my opinion, they completely skip the most important part: how to load the filament in the first place. And on top of that, their guide suggests cutting out a section of the printhead's casing. That raised another big question for me. If I adjust the extruder spring pressure and do not manage to set it back correctly, will my printer still work as expected with other materials? So here are a few answers. Instead of drilling into the housing of the printhead, you can simply remove the extruder from the printhead. Now, if you're wondering why this is a better solution, here are a few reasons. It takes only 5 minutes. All you need to do is remove 4 screws and unplug the hot end connectors. You won't void your warranty, and if you want to print super flexible materials, you should familiarize yourself with taking apart the extruder anyway. Otherwise you will end up like me. Your extruder jams and you're running around like a headless chicken because your printer suddenly stops working and you have no idea how to fix it. That's also why I've decided not to cover TPU60A in this episode. Instead, I will dedicate an entire episode to it. I don't just want to throw some slicer values at you. As I mentioned earlier, I want to show you what's happening behind the scenes. More importantly, I want to give you the right tools so you can troubleshoot problems yourself with confidence. The calibration tools we looked at today were just one piece of the puzzle. In the next episode, we have to take a closer look at the actual hardware, starting with loading the filament, how to properly adjust the extruder spring pressure, and the best way to clear a jammed extruder. To get ready for the next episode, I've got a little homework assignment for you. The goal: successfully loading the filament. To completely eliminate the resistance of the PTFE tube, we will be loading the filament directly. That means placing the spool above the printer and minimizing the unwinding resistance as much as possible. There are plenty of solutions online: wall mounts, brackets, or simply attaching the spool to an overhead object. My printer stands freely in the room, so I designed this spool holder instead. It's made of PLA parts that simply snap together and can be mounted directly on the printer. To prevent scratching the metal housing, I use TPE 83A for the contact points. These rubber elements fit snugly into the PLA parts, protecting the metal surface from scratches while also providing just the right amount of clamping force to keep everything securely in place. The spool itself is mounted on F62 3ZZ ball bearings, which in turn sit on a stainless steel rod. You will find links to the bearings, steel rod and printable files in the show notes. And for those who want to design their own solution, here are my exact spacing measurements for the spool rotation axis. Finally, before we wrap up, here are a few tools I highly recommend having on hand. A pair of tweezers with curving tips. Super handy, especially when dealing with a jammed extruder. A small side cutter. 2 hex screwdrivers, 1.5mm and 2.0mm. I personally use a set from Vera, which I can recommend. And in case you do decide to drill into your printhead housing, you will need a 2.5mm drill bit and a compact drill. I will share more details on that in the next episode. You will find affiliate links to some of these tools in the show notes. Alright, expect the next episode in about a month. If I missed anything or if you have any questions in between, let me know in the comments. As always, I hope there was something interesting in here for you. Thanks for watching, see you next time, and happy making!